So we've been looking at reactions and how we can start to use our knowledge of reactions and our coefficients to be able to start to predict how much of a substance we would get after a chemical reaction has occurred based upon the amount that we started with. The problem is though, anytime you've got more than one substance, more than one thing actually doing the reaction, we have to take into account both of those reactants. And so today we're doing a real quick refresh or a kind of reminder session on how we determine and calculate based upon our limiting reactant. So limiting reactant by definition is any substance that limits the reaction. Oh, okay. In more layman's terms, it is the substance that you run out of first, because once you run out of it, the reaction stops and you no longer can continue the reaction. As a result, you're only going to be able to make as much theoretical product as your limiting reactant allows. So not only is it the thing that runs out first, it's the thing that determines how much product you're going to get. It is essentially in charge of the reaction. And so to do this, the steps are going to be very, very similar. We're going to be doing the same sort of mathematics that we've been working before. The only difference now is we're going to have to do it more than once and figure out which of our which of our reactants makes less product. So let's take a look at one of the examples coming off of our handout. So this is on handout 3.6. I'm going to go ahead and just look and run through number 2 real quick. Number 2 on there. Good example of these types of calculations. It's a real nice one to be able to look at what's going on for our calculations. So acetylene gas, excuse me. Acetylene gas is commonly used in high temperature torches. When acetylene reacts with hydrogen, ethane gas is produced, and then we're given a balanced chemical equation. Excuse me. So what this says is that for every one ethene or acetylene molecule, we need 2 hydrogen molecules to react, and when all those 3 particles react, we end up making our ethane. And so we got to figure out in this reaction, if we start with 30.3 grams of acetylene and 4.14 grams of hydrogen, ultimately we want to know which one's going to run out first. And then based on which one runs out first, how much product we can expect to get. Now we can't compare those directly. Hydrogen is much, much lighter than our acetylene. And so we actually, first step here is going to be to get out of grams and into moles. Well, we've been doing that a whole bunch. So we got 30.3 grams of our acetylene, C2H2. We would need the molar mass of acetylene. So we'd go to the periodic table. We'd have 12.01 times 2 plus 1.008 times 2 for a total molar mass. I'm not going to show it here for sake of time. Read the right notes here. I've got a molar mass of 26.03 grams per mole of acetylene. And so when we do that math, we take our 30.3 grams, divide by our 26, we end up with 1.16 moles of our acetylene, C2H2. Cool. Now we know how many particles or moles worth of materials of acetylene that we have to react. We got to do the same thing for our hydrogen. We got 4.14 grams of our hydrogen. From the periodic table, I know the molar mass for an H2 molecule is 2.016 grams per every 1 mole. When we divide here, our grams cancel, gets us into moles. When we divide here, we end up with 2.05 moles of our hydrogen. Cool. So now we know how many particles or moles worth of both of our materials we've got in the start of our reaction. Now we got to figure out which one runs out first. And the easiest way to do this is to solve both reactants for the same product and then see which one makes less. Now the good news is part C, we can actually do kind of B and C together here, because C asks what's the maximum amount or the theoretical yield, how much ethane gas should we expect based upon these 2 mole amounts. And so we're actually going to have to do 2 problems again, but again, we're solving 2 questions at the same time. So we're saying if our acetylene is the limiting reactant, we want to know how many grams of our ethane we should expect, C2H6. But we also want to know that if we use up, if for example our hydrogen is the limiting reactant, we had 2.05 moles of hydrogen. We want to know how much theoretical ethane we would get from this. So we want to find grams of C2 C2H6 here. So we're going to set up two separate problems, but then we're going to be able to compare them, which will be really kind of nice. Cool. First step, if we're in moles of one thing, we want to change to moles of something else. Our first step is going to be our mole ratio. So from the balanced equation, I know that I have, for every 1 mole of our acetylene, we make 1 mole of our ethane. So now we can go ahead and mole ratio. Our units tell us right where our materials need to go. So for every 1 mole, so I'm going to try to squeeze this in here, of C2H2, we can make 1 mole of our ethane, C2H6. Cool. Now we need the molar mass of our ethane. Well, from the periodic table, we can add all those together. Turns out it is 30.068 grams per every 1 mole of our ethane. Moles of ethane cancel, moles of acetylene cancel. We're into grams. I'm going to put it down here at the bottom because I've kind of run out of room. Well, actually, here I can erase a little bit. Cool. So we do that math and we end up, essentially what we're saying is if, and that's the question here, if the acetylene is our limiting reactant, we should be able to make, theoretically, 34.9 grams of that C2H6 ethane. But we don't know. We got to take into account the fact that we have a certain amount of hydrogen gas. Same process, different numbers. Now our mole ratio, if we look up above, our mole ratio is for every 2 moles of hydrogen, we make 1 mole of our ethane, C2H6. Same final step for every 1 mole of ethane, C2H6. We've got a molar mass of 0.68 grams. Cool. So if I'm looking, my moles of ethane cancel, my moles of hydrogen cancel. The only unit I have left is the unit that I wanted, which was our grams of ethane. When we do this math, we multiply top and then divide by 2, we end up with 30.8 grams of our C2H6. And now we can compare. If all of our acetylene reacts, we get 34 grams, almost 35 grams. If all of our hydrogen reacts, we get 30.8 grams. And so when we add these two together, they react until all of a sudden we run out of our hydrogen. Our hydrogen runs out. It has limited the amount of product we can get. So that means our limiting reactant would be our hydrogen. Our excess would be our acetylene. And what's our theoretical yield? Well, we're going to be able to make 30.8 grams before we run out of the hydrogen. So we're able to do B and C at the same time by comparing our two amounts. Now, sometimes you don't have to go all the way to grams. Theoretically, you could have just gone to moles of ethane and then compared. Sometimes you'll have more than one product and you're like, oh, well, which one do I solve for? It doesn't matter. So if the question doesn't specify one product versus the other, just pick one product, solve them both for the same product, and compare to determine which one makes less. Your limiting reactant will limit the amount of product you can make.